Good morning, honors chemistry students. The next molecule that I would like to review with you is a very important molecule that enables us to survive on the face of the earth. In fact, enables all life to survive on the face of the earth, which would be the water molecule H2O. Keep in mind that once you've completed all your predictive paperwork and you've constructed your model, I want you to provide an illustration of that model in the second column on your Meet the Elements lab. Thirdly, when we consider this molecular geometry of the water molecule, let me flatten this out here a little bit. When you consider the molecular geometry of the water molecule, we're going to examine its AELD, or the atomic energy level diagram. Since we have 3 atoms in this molecule, it's not too hard to imagine that the central atom might very well be the oxygen atom, which has an atomic number of 8, which has 8 protons and 8 neutrons, which means that it should also have 8 electrons. The first 2 electrons go on the first energy level, which would be the 1s sublevel, and then we'll complete the remaining 6 electrons, since oxygen's in group 6a on the periodic table, by placing 2 electrons in the 2s, 1 in this 2p, 1 in that 2p, 1 in this 2p, and completing the 6 valence electrons in the oxygen atom, just like so. So oxygen has 2 lone pairs and 2 unpaired electrons. Remember that when nonmetals bond, they share the number of electrons required to reach the octet state. So we're going to represent a hydrogen atom here with its with its 1 proton, and we're going to go with the isotope of hydrogen, which is protium, which has no neutrons. Because it has 1 proton, it also has 1 electron, and we're going to represent that electron like so, and form 1 shared pair of electrons, which is otherwise known as a covalent bond. We're going to represent the second hydrogen atom here with its 1 proton and no neutrons and 1 electron, and thus the second hydrogen bonds right there. So oxygen really shares 2 of its valence electrons with 1 electron each from 2 hydrogens. The question is the extent to which these electrons are shared between oxygen and hydrogen. Are they shared equally or not equally? We'll figure that out later. Also, when you look at oxygen, from the perspective of oxygen, if I can cover up the hydrogens, you can see that oxygen's now in the octet state, and it has the pseudo configuration of neon, which has 10 valence electrons. Each hydrogen, if I can cover this up without creating shadows, each hydrogen has 2 valence electrons and assumes the duet state of helium. So in essence, we've created 2 covalent bonds, right? In doing so. So the next column we're going to look at is the orbital notation diagram. Having a little bit of surface issues here. So we're going to look at orbital notation and how we might represent this using orbital notation, which extends from atomic structure and quantum mechanics. So let's start with the central atom, oxygen, which is on actually row 2 of the periodic table and has enough electrons to start filling the second energy level. So we'll put 2 in the 1s, 2 in the 2s, and then 1 up, 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 and then 1 down. That's 6 valence electrons, or for a total of 8 electrons total for oxygen. So that being said, we need to represent the shared pair of electrons for hydrogen, and we'll do it in this fashion. We'll represent hydrogen's 1s electron here, and we'll represent the other 1s electron here. And I've placed those electrons with down arrows to show that these electrons, valence electrons that are being shared in a covalent bond, have opposite spins, theoretically. So we have 2 shared pairs of electrons, therefore, between oxygen and hydrogen. So let's go on to the electron-dot diagram. So we're going to look at the electron-dot. Wow, my paper is just kind of floppy today. It's not cooperating with me. The electron-dot diagram. All right, so we have oxygen with its 6 valence electrons, and we're going to show how hydrogen shares its valence electron there, and another hydrogen shares its valence electron there. All right, so you can clearly see that the oxygen is in the octet state, and each hydrogen is in the duet state with 2 electrons. The next diagram that I ask you to represent is the structural formula, which simply represents shared pairs of electrons with lines. So we're going to represent that structural formula in this fashion, where the lines represent 1 shared pair of electrons, or 1 covalent bond. And we can say that in the structural formula, we don't represent lone pairs of electrons like we did with the electron-dot diagram. So once that's said, let's take a look at the electrons in our molecular system, because we want to make a prediction for the arrangement of the electron pairs, and we want to make a prediction of the number of bonds. So let's start with the number of bonds. We know that oxygen has 6 valence electrons represented by the dots. Each hydrogen has 2, 6 and 2 is 8. And we want to compare that to how many electrons are actually needed to enable the molecule to be stable, or the individual atoms to be stable, perhaps better said. So oxygen needs its full complement of 8 valence electrons. Each hydrogen needs 2. 8 and 2 and 2 is 12 by my calculations. And so to predict the number of bonds that form between the oxygen and the hydrogen, we would look at the difference between 12 and 8. We have 8 valence electrons, but we need to make the 8 look like 12, which means that we're going to entertain the thought of having 4 valence electrons involved in bonds, and each bond has 2 electrons per bond. 4 divided by 2 is 2, so we would predict 2 bonds in the oxygen molecule, which is exactly what we have. So once we predict the number of bonds formed, then we need to look at the Lewis dot diagram, which is really a hybrid of the diagram between the structural formula and electron-dot diagram, in which we represent shared pairs of electrons with lines, and then we go ahead and put in the lone pairs that are present. So that's your Lewis dot diagram for water. The next column we're going to look at is really, really, really important for water, and as it is for all molecules, but we're going to examine the bond type. All right, the bond type examines the electronegativity differences between the central atom and each hydrogen. So let's look at the electronegativity of oxygen. I believe it is 3.5. And again, some of these values may be slightly different on different periodic tables or different sources, but they should be close. And the electronegativity of hydrogen is visualized or is accepted as 2.2. So 3.5 minus 2.2 is 1.3. So what does that difference in electronegativity mean? Again, if you remember back to our sliding scale between 0.0 and 0.4, a bond is classified as being nonpolar covalent, meaning that the atoms have similar electronegativities and therefore the electrons are shared equally between the two atoms. If the bond is between an electronegativity difference of 1.5 to 1.7, we say that the bond is polar covalent, meaning that there is a separation of charge that exists between the atoms in the bond. And so that classifies a difference in electronegativity of 1.3 as being polar covalent. And once again, to cap this off, if the electronegativity difference is between 1.8 or greater, we say that that bond is classified as being ionic. So what this means is that in each of these diagrams, we can theoretically view this in this fashion, that the electrons in these bonds are pulled closer to the oxygen than they are to the individual hydrogens. And so therefore, we view the oxygen as being partially negatively charged and the hydrogens as being partially positive. I put a double negative sign here because you've got two electron pairs being pulled closer to the oxygen. In real terms, what that means is one region of the molecule becomes negatively charged and the other region becomes positively charged. So we've actually set up a dipole. And what we can say is, in setting up that dipole, is that these two bonds are actually what we refer to as polar covalent bonds, meaning that because of the electronegativity difference between oxygen and hydrogen, the electrons are pulled closer to the oxygen than to the hydrogens, which leaves one end of the molecule negative, the other end positive. And so therefore we say water is a, quote, polar molecule because a dipole is created with two oppositely charged regions of the water molecule. So in keeping with that, I want you to go through on the other diagrams that we've created and always keep that in front of yourself by saying, in this case, the oxygen's negative and the hydrogens are positive. So we show that direction of electron pull towards the oxygen and away from the hydrogen in each of these diagrams to be consistent. And that is worth points on an exam, because if water were linear and not polar, we would not exist on the face of the earth, because then water would not be able to absorb that tremendous amount of heat energy from the sun with just a small rise in temperature. So that being said, the next column we're going to look at is the total pairs around the central atom of oxygen. So when we look at oxygen, we can see that there are two lone pairs and two bonded pairs. 2 and 2 is 4. So as in prior molecules, any time that the total pairs of electrons around a central atom is 4, the valence shell electron pair repulsion theory says that those electron pairs will arrange themselves to establish the minimum repulsion between the negatively charged electron pairs. So in that sense, we're going to have, Vesper theory would say, well, we have two bonded pairs that look something like this, and we have a lone pair here, and we have one behind the plane of the paper. So this bond angle that's predicted for 4 total pairs is 109.5. Remember that? 109.5. Light FM, your tetrahedral station, serving all 4 corners of Dade County, is that you don't want to go to, which would be what? Aventura, Hialeah, Kendall, and South Beach, where there's too many people. All right. So essentially you create a molecule with 4 corners or 4 faces, 1 on the front, 2 on the sides, 1 on the bottom. And we say that this is a tetrahedral arrangement. Now keep in mind that Vesper theory is really designed to explain the arrangement of electrons around a central atom and the localized electron model when they're not bonded. But there's a companion theory known as hybridization theory, which seeks to explain the arrangement of electrons around a central atom when the atoms are bonded together in a molecule. And once again, this total pairs of electrons of 4 predicts, yes, a tetrahedral geometry with a bond angle of 109.5. But what it also predicts for us is that to explain how 4 pairs of electrons arrange themselves, we say that an S overlaps with 3 P's to create 4 equivalent hybridized orbitals. So when we think about this, we're going to illustrate oxygen, and we're going to draw 4 equivalent hybridized orbitals, which are known as sp3 hybridized orbitals. We're going to show a bonding pair of electrons here with a hydrogen, another bonded pair of electrons here with another hydrogen, and the 2 lone pairs here and there with a bond angle of 109.5 light FM. And this too, in hybridization theory, predicts a tetrahedral arrangement. And the hybridization scheme that explains this arrangement of 4 total pairs of electrons is referred to as sp3. Not sp cubed, but sp3. All right, so that's something that you just really have to work on memorizing, that 4 total pairs predicts tetrahedral arrangements with a bond angle of 109.5 degrees with a hybridization of sp3. Okay? So once we get through the hybridization column, we're interested in knowing the actual geometry of the molecule, because the actual geometry is not always the same as the predicted geometry. So because we cover up the lone pairs and we only look at bonded pairs. So in this case, we'll draw our oxygen atom with our 2 bonded pairs of electrons, or the 2 bonded hydrogens, and then we're going to represent the 2 lone pairs. And keep in mind, I forgot to do something on each of these diagrams. The oxygen is slightly negatively charged. The hydrogens are slightly positive. And the same thing here. The electrons in these bonds get pulled closer to the oxygen, so it's slightly negatively charged. The hydrogens are slightly positively charged. And now what you need to appreciate is that these 2 electron pairs squeeze these bond angles down because they're similarly charged objects. They squeeze these bond angles down to a bond angle that's something less than 109.5. And theory says it's 105 degrees. And we describe this geometry not as tetrahedral, but as bent, because the molecule looks bent. So that being said, that explains why water is in fact a polar molecule, because this end is negative and this end is positive. So a dipole exists, and I could very simply write this out like this. We could say a dipole, what? Exists. Okay, so after the actual geometry, we're going to look at the bond energy once again. And you'll have to look up these values. Let's see, for water, the bond energy is 467 kilojoules per mole. That's the amount of heat energy that's released when the oxygen-hydrogen bond forms, or how much heat energy has to be supplied to break that bond. And that being said, the bond length for the oxygen-hydrogen bond is 96 picometers, all right? And we'll talk a little bit more about the significance of bond energy and bond length. And then we have our AXC system. Now this is where this starts to make some level of sense, because what we're looking at, the A represents the central atom. The X represents how many bonded pairs, and the E represents how many lone pairs. So we have a central atom, which has 2 bonded pairs and 2 lone pairs. So we say that the water molecule is an AX2E2 molecule, okay? And is thus bent. So molecules typically that are AX2E2 are bent molecules. And last but not least, when we look at the polarity of water, decidedly water has 2 polar bonds, and the molecule itself is considered to be polar because of the opposite charges on either end of the molecule, creating 2 different charged poles. So with that being said, the next molecule we're going to look at is CH4, or methane.